Hi, and welcome to a little quickie video. I'd like to start by saying that I've started my treatment for the prostate cancer, the radiology treatments, and things are going very well. I am, however, getting tired, so I need to rest a little more, and that's fine. So I'm going to break away from the vlog project for a few days, because those long project videos, they require a lot of time and a lot of work to get them together. One of those 40-minute videos can easily take me 25 hours of work. And I'm not complaining because really I enjoy doing it, but I just want to take a little break, so next week I'll be getting back into that project. But for now, I felt like producing a little quickie for a good friend of mine, Jackie, a guy who lives in France, and who produces scale models, mostly, but not exclusively, steam powered. And he does extraordinary work. And what is amazing about it is that he does it with very little formal training. I mean, he begs, borrows, and steals information. I don't think he steals it, but he gets information whatever way he can, and he tries to learn how to do things. And he gets incredible results. So I invite you to go and take a look at his not his web page, but his YouTube page. Here's the name of it, Modelist Motorist. And even if I know most of you who are watching the English version of this video won't understand French, and that's fine, I just invite you to go see what he does, because you don't need to speak French to appreciate the quality of the small things that he produces. So he asked me a question because he's having problems with producing really a tiny crankshaft he needs. And he's been producing it in odd ways, trying to get a handle on how he could do it. But he would really like to produce it from a solid part. And I let him know that, hey, I think I can help you. And he sent me a copy of a sketch that he made of what he needs, and a few pictures. So let's take a few minutes and go and take a look at this sketch and the pictures that he sent. So let's start with the sketch. Now we can see that we have a 3-lobe crankshaft, or if you prefer, we have a main that's 8 millimeters in diameter, and we have 2 eccentric lobes that are each 12 millimeters in diameter, and they are offset by approximately 2 millimeters. I say approximately because they're offset in X and Y simultaneously, so it's not really 2 millimeters. And we'll calculate that a little later. So just to give an idea of dimensions here, the main or the offset lobes, the eccentrics, are 12 millimeters in diameter. And 12 millimeters for us North Americans is really just under a ½ inch. So these are tiny parts, and this is one small crank. Jackie tried 2 methods to produce this part. The first was to produce each lobe separately and to braze them together. And as we can see, well, that method did work, but it remains a shoot and miss technique, and Jackie would like to be able to produce his parts with a little more precision, and if possible, in one piece. Jackie then tried to produce a lathe fixture, and this idea could have functioned, but the design was a little iffy, and he was getting eccentricity problems. Not that it wasn't eccentric, it just wasn't at the right level of eccentricity, as we can see on this picture of a test piece where we can see a double cut on the main lobe. Well, before we go any further, if we want it to be accurate, well, we're going to have to get some numbers. And there is enough information on the sketch, and that's well done, because there is just enough information, and that's the way it should be, to figure out my positions here. Now, I have a rough sketch with orange and purple being the 2 eccentric lobes, and red here being the central lobe. Now, I have a sketch here that shows the 3 center positions of each of the 3 diameters. But I need to know, if I want to do it accurately, where those positions are. So with a little trick I can figure it out. Now he's told me, I got the center lobe a little larger here, he's told me on the sketch that the hypotenuse of a 30-degree triangle that this creates is 2 millimeters. This is tiny, tiny stuff. Okay, 2 millimeters. Well, with sine, I can calculate that sine of 30 degrees is opposite x, I don't know, over hypotenuse 2. So sine 30 degrees is x over 2. And if I work that out, the answer is that the opposite side of this triangle is 1 millimeter. The adjacent side of the 30-degree triangle here, I have to figure out as well. And for that I can use cosine. So cosine of 30 degrees is adjacent over hypotenuse, and x is the adjacent one here. And if I calculate that out, well, I end up with an adjacent side of this 30-degree triangle at 1.73 millimeters. It's actually 1.732, but I think we can forget about the 0.002 of a millimeter here. So I have my numbers, and what I need to do now is to lay out and produce center holes accurately on the end of the part here. And that is the trick. It's how to lay them out without losing our reference. Because I have to lay them out in my first example, we're going to be producing this part between centers. Well, we won't be. I'll explain its production between centers. And we're going to be producing these three center positions on each end of the part, and they have to be positioned the same way. And the trick here is to produce a small flat. Now I've exaggerated in black here my rough material. I could use a lot smaller than that. But what's important here is that I've produced a flat on this very short bar. I could have also used square stock. And because I have a flat there, I can rest it on a surface plate, and I can, with a height gauge, come and lay out a line for my two offset lobes and another line for the height position of the center lobe. And then I could take this flat and turn it sideways up against an angle plate, and with the side of the part leaning on the surface plate, and lay out two lines or three lines, one showing the center axis and one for each offset axis. And that would give me three positions, three crosshairs, that I could then use to position a center drill in the proper place, using very attentively a prick punch and a center punch, and Lord knows with these sizes, a magnifying glass. So I don't think I need to mention that the first thing you want to do here is not drill out the center hole, because if you did, well, you'd have no meat left to put these center marks and eventually center holes into your part to be able to hold it between centers for those three lobes. And in the first example, we had a flat on our piece of stock that we could lean up against or rest on the surface plate to lay out my lines in one plane, and then rest on surface plate and the flat up against an angle plate to lay out my lines in the other plane, one on each side of the part, one layout on each side of the part, each end I should say. Well, that's not the only way you can do this. If you don't want to produce a flat because, hey, you're above all that, well, you can use, if you have it, an accurate vise, something like this, a small toolmaker's vise, because it's indexable. And that means that I can use it sitting down, or laying up, or on its side. And if I clamp my part into it, as you can see here, well, I can rest it there, lay out my line in one plane, and then come up and lay out my lines in the other plane. And that will work as well. So why did I talk about the first method, producing a flat? Well, not everyone has a vise like this, and this, using the vise technique here, it will do it accurately, but it does have one problem, and that is it's irreversible. Once I take my part out of this vise, I lose my orientation in the rotation of the part. In other words, I can't come back and rescribe those lines accurately. Whereas if I use the flat, I can always backtrack, come and adjust. So there's plus or minuses, producing a flat or not producing a flat. But once I have those positions laid out, I'm going to very attentively punch them and center drill them and move on to holding it between centers. But there's another way of doing this, another way that doesn't entail producing center holes on each end, but we will produce holes on one end of the part, and for that we'll head over to the mill to take a look. Now in the mill we can do something that we couldn't do with the layout table, and that is ensure that my holes are very, very accurately positioned. And here's a video that I produced for positioning holes accurately on a mill that doesn't have a digital readout. In other words, using the graduated collars and taking backlash into account. But if you have a digital readout, well, this is deathly simple. So we could set up our part in the machine and indicate find its center or wherever we want to position that first hole, and then move from there to produce the two eccentric lobes, the two positions on that. And I could produce my center holes, and if I start with a square part, well, I could flip it over easily, or a part with a flat on it. I could flip it over without turning it and do the same pattern on the other end and then go turn between centers. But there's a way that I can use a 4-jaw chuck on the lathe to do this as well. The problem is figuring out where I have to offset my 4-jaw, and that can be problematic. Now, for this operation, you're going to want to use a square piece to start off with, because when you offset the part in the 4-jaw chuck, well, if it's round, especially small as it is, you're going to end up with problems of running into the sides of jaws and sliding off the jaws or holding just on one edge of the jaw, and that becomes very daunting. If your part is square, even if it's small, you can move sideways, up and down, and just without tightening the jaws to death, you can move your part and keep everything nice and even and move it easily, especially if you use some kind of intermediate shim there to permit the part to slide easier. So that would be a great suggestion, use a square part. And if we're going to use the 4-jaw, well, we don't need my holes on each end. We'll produce the pattern of 3 holes on one end only. Now this is a tiny part, so in this case we're going to have to produce quite accurate, about 1.5 millimeter holes for it to fit properly. Not center holes, finished parallel accurate 1.5 millimeter holes. If this were imperial, we'd be looking somewhere around a 1/16. And we're going to drill those and ream those to get them exactly at the right diameter, because what we're going to do then is take this part with the 3 drilled accurate holes in the end, go over to the lathe, set it up in the 4-jaw with the opposite end that doesn't have the holes in it mounted in the jaws, and then I'm going to put a pin in one of the holes. Preferably in this case, probably start with the central lobe and put a pin in that corresponding hole, put an indicator on that pin close to where it enters the part. I don't want to indicate the end of the pin, there could be a little wobble there, so come right up close and indicate that pin to 0 by adjusting your 4-jaw chuck. And you will be pretty darn close, if you're attentive, within 1/1000th of an inch of the center axis of that first lobe, and you can cut away till your heart's content and produce that first lobe. Then what do? Well, extract the pin. You don't want a press fit, you want a snug fit. Extract the pin and then move over to the next hole, which would be the second lobe, and indicate that to 0. And that means that your part will be offset so that that axis is on center, and turn your second lobe. And do the same for the third. And your part will have its 3 lobes quite accurately positioned with an accurate indicator, an accurate pin, and 3 accurate holes. An indicator like this older than I am, started last word, that I really enjoy using, even if it's not the most practical small indicator. There's something very romantic about using old tools like this. Okay, so we can do it that way with the forejaw, but for that you have to use a square part. It's just not practical to offset in the forejaw a round part like that and expect to get it accurate. Well, why do we look at the first and turn between centers? Again, there's advantages. The center, turning between centers, is more daunting, more setup work, more organization. But once it's done, and you can move on through your project, backtrack, take your part out of the machine, put it back into the machine, do what you want when you're holding it between centers. Unless you move the tailstock of the machine sideways or out of axis, it's going to always come to the same position if you reposition it between centers. And that is a great advantage, because if you were producing several of these parts, well, you would save an awful lot of tool changes. And what do I mean by that? Well, imagine you set up between centers, you turn your first lobe, you move to the next set of centered holes, you turn your second lobe. You move to the third set, you turn your third lobe. You've done all 3 in a matter of minutes without moving your tool, because they're all turning and facing operations. Great! Now you have some grooving to do on the 2 offset lobes. Well, you can set up a grooving tool. You can go back to the centers of the first offset lobe, groove that one, move on to the centers of the second offset lobe, groove that one, and save a lot of time. You've only had 1 tool change. Now imagine if you had 20 of these parts to do, the holding between centers would save you tons of time, and if you're working for money, make you a lot of moolah. But if you're doing just 1 part, and an extra tool change really isn't going to make much difference, or 2, 3 tool changes actually, well, this method of drilling holes just on one end and using the forejaw will work just fine. There are many other ways of doing that. If you're courageous, you can omit all the center holes and just go straight to offsetting your forejaw chuck using your cross slide to measure how much you're offsetting. So here we have our square part, our indicator set on 0 on the low spot of that surface. You can see there, that's the low spot. So we're going to come off, turn over to the opposite side, come back on. Now I'm just barely touching it, and there I can see that we're within about half a thou. That's the low spot of the opposite side. So these are centered. Come off, come over, quarter turn, come back on, find the low spot, and we see that we're there again. So if I have 3 surfaces of this square part on the same 0, well, I don't have to check the 4th one. It's going to be on 0 also. So I know that my square part here is centered, and now I want to offset it by 100,000ths of an inch. So I have my comparator in contact with the low spot of that surface. It's set on 0, and my backlash for my transverse axis here is taken up on my side. So that's everything fine. I can move that direction without any backlash. I've set my collar to 0, and what I want to do is advance 100 thou. So I'm going to pull the comparator off of the part with the longitudinal axis and move 100,000ths of an inch, 0.1, in that direction without contacting the part. Now, this is very important. My dial here, or my transverse axis, cuts on the radius. So that means that if I move 100 thou on my graduated collar, my tool will actually move 100,000ths of an inch. If, however, your lathe cuts on the diameter, well, you're going to have to double that dimension. So you're going to have to move 200,000ths of an inch to get your tool to actually move 100,000ths of an inch. So let's pull that away on with my longitudinal axis and take a look at how this is done. So I have here a drill that's about 100 thousandths of an inch in diameter, approximately. We're just guesstimating here to start. I'm going to back the jaw off here so that this just fits in between the space between the jaw and the part. And that means that I'll have backed that jaw off about 100 thousandths of an inch. Then I'm going to move the part forward, or back, depending on how you're looking at this, to just barely come in contact with the jaw that I've backed off. That'll put me a little bit close, or a little past probably the 100 thou that I want to offset. Then I'm going to come back onto the part with my dial and fine tune it to come back to the 0 that I had on the dial. So let's take a look at that. So there, our part is quite accurately offset by 100 thousandths of an inch. It's really not that bad, but if you're doing a single eccentric cam, well, this is a viable way of doing it. We've just seen it's not very complicated. But we have a problem here. If we're doing 2 lobes, well, we have to offset in one direction, as we've seen then just now, and then we're going to have to come back in the other direction. That's already a little more complicated. But in the example that we're looking at today, Jackie's double-lobed eccentric, well, both lobes are eccentric in 2 planes. So I don't have to, because usually a crankshaft, or many crankshafts, have all their lobes on the same plane. You offset one way and come back for the other. It's that basic. But in this case, each lobe is offset in 2 planes. And that means that I'd have to offset both directions for each one. And that starts to get pretty complicated. So in Jackie's case, I would truly suggest the first method we talked about, where we hold between center, or the second method where we indicate a pin that we position in the end of the part to get this job done. Now, I hope that helps you, Jackie. And I would love to get pictures sent to me of the finished part if it does work. But for everyone else, have fun, be safe, and happy machining.
There you go.